Nine, how's everybody doing today? So we're going to talk a little bit about controlling the flow of electrical current, something that we pretty much take for granted on a daily basis. So we'll get into that now in a moment. Okay, so you may recall that we have two types of materials. We have insulators and we have conductors. So insulators will basically prevent the flow of electricity and they don't conduct electricity, whereas conductors, of course, allow the free flow of electrons and so on. So these are typically metals and these are typically non-metals. Okay, so if we look at something like copper here, we have good conductor, so we can basically have free and easy movement of electrons. And even with a semiconductor, which in this case would be silicon, but you can also have carbon or graphite would be an example. You don't have as many electrons available to carry that charge. And of course, we have nonmetals, which would be an insulator. So in this case, we have glass, although glass is a good conductor of heat. It's just not a very good conductor of electricity. Okay. So if you think about electrolyte solutions, like even Powerade or Gatorade, for example, we will have ions available that will be able to carry charge. And this is why we call them electrolytes. So the more of those we have in there, the more conductivity we can have. So if we have pure water, we shouldn't be able to conduct electricity, right? So however, tap water is not pure. It does have some dissolved ions in it. It does have some naturally occurring electrolytes, so it will conduct electricity. So just a little bit about conducting electricity. So neon signs, of course, you may be familiar with. And a neon sign is basically when we send an electrical current through neon gas, which is one of the noble gases, right? So typically these are insulators, but if we apply a current to it, it actually excites the electrons that are within the atom, and these become free. So once they become free and they have been excited, they do emit a particular light, a color of light, I should say. So you have a mixture of charged particles which can conduct electricity. So different gases will emit different colors of light, and this is very similar to what we get with the northern lights or the aurora borealis. So here are some examples. Of course, you've got the noble gases right here, and they make for some interesting signage. So we talked about conductors, insulators. In between, we have semiconductors. So if we get these heated up, they will act like conductors. And at lower temperatures, they act like insulators. So a couple of those would be germanium and silicon. And silicon, of course, you may already know, is one of the major components of microchips and microprocessors. Okay. So superconductors are perfect conductors. They have no resistance. So typically materials will have some resistance there. One material that you should be familiar with having resistance, well, a couple of materials. One will be an incandescent light bulb. So the tungsten filament, there will be resistance when we send electricity through it. So that resistance will cause the material to heat up and eventually glow, which will produce the light that we see. Also, inside of a heating element, so this you could find in the stove. So when we send electricity through that element, there's enough resistance there to basically cause it to glow. So consider the material basically gets in the way of the free and easy movement of the electrons. And basically, you want to consider that it's rubbing up against that material. And as it does, it produces friction. And then that friction becomes heat. And then we get a glowing of that element. So have a look at this superconducting levitation video. It's very interesting. Combine some of the things that you probably already know about magnets as well, and just very interesting properties. Okay, so of course resistance is basically to do with how difficult it is for electrons to flow. If we make it difficult for electrons to flow, we can generate heat that way. And we take advantage of that, of course, in the examples that I talked about with the incandescent light bulb and the heating elements, right? So even space heaters will take advantage of that as well. So high resistance will create heat or light. So we do have resistors, and one of the main jobs of a resistor is to limit the amount of current. So these are some simple resistors, and these lines will actually tell us how much resistance is available there. Sometimes we just want the current to be slowed down just a certain amount, right? Now you can also have variable resistors, and they change how much resistance is available, and we'll get into how that is applied or how that is used in daily life here now in a moment. Okay, so just take a look at your textbook at page 301 and look at how the polygraph works. So of course, some of the applications of resistors and even with switches. With a switch, we can basically turn off a light, for example, and it's completely off. In some cases, we want to have some of that light still available for us. So like consider a dimmer switch. Okay, so we wanted to change the flow of electrons gradually. We can use a variable resistor or a rheostat. So on page 301, they actually show you how to make your own dimmer switch. I mean, if you have the materials there, it doesn't seem like much. But again, like if you do have the materials, you could definitely attempt to make this dimmer switch, which is kind of interesting, right? There's not a lot of materials required there. So either way, so with the dimmer switch, we have a variable resistor. And so if we want the light to be bright, we would keep the resistance low. And if we want the light to dim, we'll increase the resistance. Okay, so again, try the QuickLab if you have the materials, and please take a look at page 303 and look through 1 to 3 and 5 through 9. These are not assignments, but these are questions that you should be able to answer. There will be an assignment on the Google Classroom, which will just be a Google form, which will cover all of Chapter 2 material. And that will be put up on the site later on this week. So we'll look at how we model and measure electricity. So if we're modeling voltage, one of the ways that we do that is because voltage is the potential energy, we'll say, behind the electrical charge, we often use gravitational analogies, we'll say. So gravitational potential energy is referring to elevation. So the higher up an object is, the greater its potential energy. So electricity is not going to flow if there isn't a change in electrical potential. So whenever we look at voltage, even if we're looking at small batteries like 1.5 volts, it has a very small potential. But then, of course, we look at something like a 9-volt battery, which has a much larger potential. And then, of course, 12-volt batteries and so on and so on. So the voltage is actually the amount of potential between basically where the electrons are and where they want to go. So one of the other ways that we model resistance then and current, and this would be on page 305, is comparing it to the flow of water. So resistance, if we consider the size of pipe, determines the amount of water that can flow through it. The amount of resistance in a circuit determines the size of the current. So if we have a lot of resistance, then that will, of course, make the current much less. And if we have very little resistance, then that means our current will be able to move much faster. Okay, so because of this relationship between resistance and current and voltage, George Simon Ohm came up with what we now know as Ohm's law. So he related current, resistance, and voltage together. And so basically what he said was at constant temperature, the resistance of a conductor will stay constant. Okay, so if we were to heat this up or cool this down, that is going to affect the resistance and the conductivity, of course, because as we heat things up, we cause particles to vibrate or start to move more, and that could potentially increase our resistance. And if we cool it down, then of course we can affect the resistance. So this is why the temperature needs to stay the same. So the current is also directly proportional to the voltage applied. And you can see this on page 306. Okay, so there's 3 different ways of looking at this. If you're calculating voltage, you will need the current and the resistance. If you're looking for current, you'll need the voltage and the resistance. If you're looking for resistance, you'll need voltage and the current. So of course, V is for voltage or volts, and I is the current in amperes, which is in A. This is just slightly confusing here. But resistance is in ohms, and this is the uppercase letter omega. Okay, so you want to try out a few problems here on page 307. I would attempt those just after going through this quick demo here. So I would highly recommend using Ohm's law magic triangle, and you've probably seen these before. But basically, the way these work is whichever of these you are looking for. So if you're looking for current, you need to cover up current. So if we cover up current, then that means we're going to divide our voltage by our resistance. Okay, so that's basically what we're getting right here. And if we wanted to get voltage, so we cover voltage, we're going to multiply our current by our resistance. If we're looking for resistance, we're going to divide our voltage by our current. There's also an Ohm's law simulator that I recommend that you try, and this will take you to another site. So definitely worth trying out. Okay, so as I was saying, if the temperature of a resistor changes, the resistance will change as well. And as I was saying, if we keep things cool, then the resistance is going to be low. But as the temperature increases, so does the resistance, because of course you have all those particles that are going to have that added kinetic energy. They're going to start moving. So we have different types of resistors for different applications, especially electronics. So different styles, sizes, and shapes. So in that past slide where I pointed to the lines, that basically gives you an indication of the different types of resistors. And if you've ever taken apart any electronics, you may have noticed these already, right? So two most common are the wire wound and the carbon composition types. Okay. So the wire wound ones, which you may have seen, longer and thinner the wire, the higher the resistance. And as I said, even these color bands will indicate some difference and variety in those resistors.